Alright, good day guys. What we are dealing with matrix in the by application of the Gauss Jordan elimination. It also has rules that we need to follow. Now the rule is much more a little bit similar to that of Gaussian elimination. But the two difference between them is that Gaussian elimination you just need to break some things down to get the last term. Then use a back substitution, which we usually call row echelon form. You get that's for Gaussian elimination. But for Gauss Jordan, you don't need to use any equation again. It tells you that break this thing finally down for me, pick my answer straight away from it. And that point we are reducing it to what the reduced row echelon form. If you don't understand what we meant by this, go and check my videos. I've talked about everything there. So my previous video rather. So what are the rules that we need to use? We know surely we need to write the augmented matrix. Then the second thing we know that now you see what you have to notice is that you have to follow the same pattern of Gaussian elimination method to get the last term. Just like that part of before we start writing the substitution, the back substitution. So use elementary row operation to write the matrix in the reduced row echelon form. That's with the help of the elementary row. So how do we do that? The first thing is that you eliminate x variable in all the row except from row 1. Now you can see that it's a little bit similar but different then. And the second thing is that you eliminate the y variable in all the row except in row 1 and row 2. Then you have to continue following this pattern until the matrix does not get to row echelon form, using elementary row operation. Then from that point, look at this important thing is that you make sure that you start from the lowest non-zero row. The row that doesn't have 0 but at the lowest row. You get what I'm saying? But a row that is lower, that's literally from 1, something like that, but not a 0 row. So you begin eliminating the variable further right from what? The rows that are above. Now the last thing is that you continue following this pattern until you get to the reduced row echelon form. That's the last breaking down. Like I said, if you are having a doubt on what reduced row echelon form is, go and check my videos. I've explained those ones already before. So we need to put this in the what do they call it? Augmented matrix form. So this would be equals to, this would be 1, -2, 3, then we have 9. This will be -1, 3, 0, -4, 2, -5, 5, 17. So from this point now we have to make sure we find a way. And I feel like we are good with our 1 at the top here. You should know when you are dealing with elementary row operation, you are looking for a way at which all this turns to 1, and literally this becomes 0, this becomes 1. And I gave you guys like I told you that from the Gauss elimination method, it could really help a lot while we are dealing with this. And what does the Gauss tells us first is that make sure this one is 1. After that, find a way to turn this one back to 0. And how can we turn this one to 0? This is actually much more qualitative to be easier. So under row 2, we can say row 1 plus row 2. You get what I'm saying? So we can say row 1 plus row 2. So we have 1, -2, 3, then we have 9. So 1 minus 1 you have 0. -2 plus 3 you have -2 plus 3 you have 1. Then 3 plus 2 plus 0 you have 3. 9 minus 4, that gives us 5. Then you have your 2, -5, 5, then 17. So we are still on the same run. So what does the next law tells us? After this one becomes 0, all the straight vertical, then this becomes 0 also. That is like the step at which we are like the logic that you could follow from Gaussian elimination method. So how do we make this one become 0? Then you have to think extensively. That how can this also turn to 0? Then something popped into your mind. You can easily say that under row 3, if you multiply row 1 by 2, then subtract it from row 3, you could get row 3 to be 0. That's this first point here. And if you were to look at what is being said in the law tells us that you have to eliminate all s variable except from row 1. We have to eliminate all the s variable except from row 1. So that is what we are trying to do first and foremost. So from there you have 2 times row 1 minus row 3. So we have this under row 3 doesn't affect 1, -2, have 3 and 9. So we have 0, 1, 3, and 5. So 2 times 2 minus 2, that gives us 0. 2 times negative to negative 4, minus times minus plus, negative 4, this gives us 1. 2 times 3, 6, 6 minus 5, this gives us 1. Then 2 times 8, you have 2 times 9, you have 18. 18 minus 17, this gives us 1. So do not forget, we look for a way to make sure that this also becomes 0 at the normal elementary row operation. Now, at that point now, we could easily just say row 2 minus, so under row 3, you could just say row 2 minus row 3. So 1, negative 2, 3, we have 9, 0, 1, 3, we have 5. So from there, 0, 1 minus 1, 0, 3 minus 1, you have 2. Then 5 minus 1, this gives us 4. So at this point now, this is the row. Okay, we are not done yet to even break it down into row echelon form. So to make the final then, we have to make this one look, this one also becomes 1. So from there we could just easily say that under row 3 multiplied by 1 over 2. So at that point I have 1, negative 2, 3. I have 9, 0, 1, 3. I have 5, then 0. Because 0 times everything here gives us 0, 0, 0. Then 1 over 2 times this, you have 1, then you have what? 2. That's 4 times 1 over 2. So this is the row echelon form that we're talking about. Then now we have to break it down to the reduced row echelon form. That is, at this point, what we call reduced row echelon form, we don't want anything like numbers there, number aside from the value you want to find. That is, my x here must be x direct. All these ones are going to be like blockage by you putting substitution. We don't want that in. That is why it is Gauss Jordan. You go straight. It is the matrix you are going to solve all your answer directly. You don't need of any substitution. If you have to use substitution when you get to here, putting them as Gauss Jordan, it will be cancelled because that is not Gauss Jordan. So at that point now, we need to keep breaking down more, by operating. So we need to make all this other one become 0. And how do you do that? You can just easily do that from here to this one becomes 0. This can become 0 from here. We can say 3 times row 3 minus row 2. So under row 2, we can say 3 times row 3 minus row 2. Are you get what I'm saying? So we have 1 minus 2, 3, then we have 9. So 3 times 0, we have 0 minus 0 is a 0. 3 times 0 minus 1, we have negative 1. Oh, this will cause a little bit issue, and we don't want that. So let's assume you said, so as to make sure there's no issue, let's reverse it. Let's say R2 minus 3 R1 and R3. This will be much more easier. So 0 minus 0, 0, 1 minus 0, you have 1. Then 3 minus 3, don't forget, that gives us 0. Then 5 minus 3 times 2 minus 6, 5 minus 6, that gives us negative 1. So you have 0, 0, 1, then 2. This has become 0. We need to make sure this 2 also becomes 0. Are you with me? So how do we tend to make this become 0 also? This one too could become 0. Same method. Under row 1, we can say that row 1 minus 3 times row 3. See that same method. So from here now I have 1 minus 0, I have 1, minus 2 minus 0, I have still my negative 2. 3 times minus 3, you have 0. Then 9 minus, for 3 times 2, you have negative 6. 9 minus 6, that gives us 3. So nothing happens here. 0, 1, 0, then negative 1, 0, 0, 1, then 2. So from that point of view, now to look at now, this becomes 0. So I need to break this one to 0 as the last thing. So I could easily say that under row 1, let's say I said row 1 plus row 2. 1 plus 0, so will you work that out? No. Let's multiply this by 2 to balance the setup. So row 1 plus, under row 1 now, 0 times this will give you 0. 1 plus 0, you have 1. 2 times 1, you have 2, minus 2 plus 2, you have 0. So this is 0, so do not forget. You have 3, this is 0, 1, 0, negative 1. Okay, so we are not yet done, sorry. 2 times negative 1, you have negative 2. So 3 minus negative 2. 3 minus 2, you have 1. So 0, 0, 1, then 2. So you can see it is straightforward. From here now, our z will be equals to 2. Our y will be equals to negative 1. And our x will be equals to 1. So you can see that there is no need of using a back substitution, unlike the Gaussian elimination method. So this is like a little bit touch of what you need to understand about Gaussian elimination method.